So in this video, we're going to introduce the fundamental theorem of calculus. For now, we're just going to introduce the theorem, and then in your homework, I'll include a proof of the theorem instead of doing a separate video for it. So here's the idea behind the fundamental theorem of calculus. So what have we learned so far? We've learned that we can estimate a signed area by calculating a Riemann sum with n rectangles. So we take the height of the rectangle times the width of the rectangle for each of the n rectangles, and we add them all up, and that gives us an estimate. And then what we've identified is that if we want the exact area under the curve, that we calculate the limit as n goes to infinity of the Riemann sum. And then what we did in the last homework assignment is we gave this limit a name. We said this limit gives us the exact signed area under the curve, and we're going to call it a definite integral. So we took that limit, the limit as the number of rectangles goes to infinity of our Riemann sum, which is just adding up the areas, the signed areas of rectangles. We have heights times widths, and we said we're going to use antiderivative notation to represent that. So we're going to call it the integral from a to b of f of x dx, where a and b come from the closed interval over which you're calculating the signed area under the curve. So the idea is that to find this definite integral, to find the signed area under the curve, we would like not to have to calculate the limit on a Riemann sum every time. So if you didn't discover this from the previous homework assignment, taking the limit as n goes to infinity of the Riemann sum can be a bit tedious. And so what we want is a shortcut for making this calculation, and that's what the fundamental theorem of calculus does for us. So the fundamental theorem of calculus says, hey, let your function be continuous over a closed interval from a to b, and let big F of x be any antiderivative of f of x. So remember, when we first introduced antiderivatives, we did f of x, the antiderivative, plus a constant of integration. So with the fundamental theorem of calculus, we're not worried about that constant of integration. We're just saying, hey, find any antiderivative. And then the fundamental theorem of calculus claims that if we want to find the signed area under the curve of f of x over the closed interval from a to b, instead of calculating the limit as n goes to infinity on a Riemann sum, we can take any antiderivative of f and evaluate it at the upper bound of integration minus that same antiderivative of little f evaluated at the lower limit of integration. So we can use, instead of calculating the limit on a Riemann sum, we can just use an antiderivative of the function in order to calculate that signed area under the curve. And the typical notation for this, and we'll show examples of applying the fundamental theorem of calculus in subsequent videos, but the notation is, hey, to calculate the definite integral from a to b, just find any antiderivative, and then we usually draw in a vertical bar and put the lower and upper bounds of integration. And after we've done the integration to get an antiderivative of little f, we then evaluate the antiderivative at b minus the antiderivative evaluated at a. So this is the fundamental theorem of calculus. The fundamental theorem says, to calculate the signed area under the curve, we merely need to find an antiderivative and then take the difference between the antiderivative, evaluate it to the upper and lower bounds of integration, instead of having to take the limit on a Riemann sum. So again, I will do a proof video for this later, but for now what I'm going to do is put an empty placeholder for the proof video in your homework, and I'll put a proof of the fundamental theorem of calculus typed directly into the second page of your homework assignment.